Okay. All right. This is our assignment 4 on micromechanics. Oh, on micromechanics on an analysis on different composites and carbon fibers.
Okay, so the first part of the assignment was to derive Poisson's ratio for a composite. So first off, we need to assume that the material is homogeneous, so that there's no significant changes throughout the materials. We have to also assume that it is linear, meaning it abides by Hooke's law, and it's also elastic, and with no body moments or defects to disturb any of the properties of the materials. So first off, we started with the basic formula of Poisson's ratio equals the transverse lateral strain over the longitudinal strain. From there, you can rearrange the equation to the change in L, which equals negative the initial length times the transverse strain. From there, you can substitute in for the transverse strain.
So can you indicate what is delta L and delta L in the
So this is the
picture that we have?
Yeah, delta L is the change in or like the deformation basically, and L is the initial length of the material.
Yeah, but there is a change in length in both the directions, right? So
Right. So there's a change in X, and there's also a change in L.
Okay.
But we're just starting with. You can start either with
Sure.
longitudinal. If this was X, then that would
yeah,
work.
you mark L over there.
Yeah. So I'm just using L for an example here. So from there, you can see that we rearranged it to the change in L equals the initial L, negative the initial L times the transverse strain. From there, you can substitute the Poisson's ratio multiplied by the longitudinal strain in for the tangential strain coming from this first equation here. Then you need to assume that there's no significant boundary interactions to use this equation here, because if there is a change in the length of the fiber, that can also affect the change in the length of the matrix as well, if we don't assume that there aren't any significant boundary interactions. So from there, you can substitute the change in L's for each of the terms. And so what you get here on this on the right-hand side is the initial length times Poisson's ratio multiplied by the longitudinal strain equals the Poisson's ratio of the matrix multiplied by the longitudinal strain multiplied by the initial length multiplied by the volumetric fraction of the matrix. And then plus the Poisson's ratio of the fraction times the longitudinal strain times the initial length multiplied by the volumetric fraction of the fiber. Then from there you can just divide out the initial length and also the longitudinal strain, and you get that the Poisson's ratio is equal to the Poisson's ratio of the matrix multiplied by the volumetric fraction of the matrix plus the Poisson's ratio of the fiber times the volumetric fraction of the fiber. Okay, so next we derived the shear modulus for a composite. So again, first we started with the same sort of assumptions. We want to assume that it's homogeneous, that it's a linear material, elastic material, with no body moments or defects. And then we also want to assume that the material is isotropic, so no matter which way it is loaded, the material properties will remain the same. So using that assumption, we can start with the shear is equal to the shear strain times the shear modulus. And then rearranging that for both the fiber and the matrix. That's what follows there. And then a second equation we can use is that the shear strain is equal to the shear deformation divided by the initial length. So this is L, this is the shear deformation. Then we can rearrange.
The shear strain is, remember, so can you just argue it out why it's correct, but remember that shear strain definition is different from the normal strain definition in terms of a change in length divided by L, which is what the normal strain was, which was okay when you presented in the previous slide.
Yeah.
But now we're talking the shear strain. So why does it turn out to be a change in length divided by L? There is an argument behind that.
So the shear
Your figure maybe you can.
Right. So basically the normal strain would be a change in L divided by the initial length. But in this case, since the shear strain is an angle, we're looking at a change in the transverse direction divided by the initial length. So that would be equal to the shear strain.
It's essentially the change in the right angle, which is the theta that you have. Okay?
Yes, yeah.
And so an additional assumption that you're making is that theta is small. So only then you can take it as same as tan theta.
Right.
Just remember delta x by L, according to trigonometry of that triangle, will be your tan theta.
Yeah.
But you're assuming it to be theta itself.
Mm-hmm. Okay, yeah. So rearranging that equation, you get that the deformation is equal to the, in the transverse direction, is equal to the shear strain multiplied by the initial length. And then you can sort of see the application for the fiber and also the matrix. And in each case, we multiply by the volumetric fraction, either by the fiber or the matrix. Again, you want to assume that there are no significant boundary interactions for this. So by the equation, delta x equals delta x of the fiber plus the delta x of the matrix. Again, if there are significant boundary interactions, then one can affect the other, vice versa. And so for there, we can substitute in for delta x using the above equations. So basically gamma times the initial length is equal to gamma of the matrix times the length multiplied by the volumetric fraction of the matrix plus the gamma of the fiber times the length multiplied by the volumetric fraction of the fiber. And so if you divide everything by the length, you get this equation over here, which is sort of analogous to the rule of mixtures. Then from there, you can also see that we're basically using those equations up here, and we're just bringing them down here. And so we're basically substituting this equation into this equation over here. And so from there, we get that the shear divided by the shear modulus is equal to the shear divided by the shear modulus of the matrix multiplied by the volume fraction again of the matrix, and the same thing for the fiber. Dividing everything by the shear gives you 1 over GLT, and we want to find GLT. So basically what we did here was we just combined and multiplied it out basically over here, and then over here we again simplified it so that it has a common denominator, and then just took the inverse, and we get that GLT is equal to G of the fiber times G of the matrix divided by the volumetric fraction of the matrix times the shear modulus of the fiber plus the volumetric matrix of the fiber times the shear modulus of the matrix.
Why do I explain this much? In particular, I like the way you highlighted the assumptions, because that was one of the important points of this whole exercise, to make sure what is the role that these assumptions play, and I think you highlighted it very well. Thank you.
So for the next part of the homework assignment, we basically compiled a list of fibers. We found their properties such as their Young's modulus, Poisson's ratio, density, and tensile strength. And we were able to use those properties to find the strength, stiffness, and buckling performance of each fiber. So here's the first part of the list of fibers. We had about 15 total for each matrix, so it totaled to around 30. But you can flip through and see we have a bunch of different fibers, like carbon fibers, glass fibers, ceramics, a large variety. And then for the first part, we have the fibers within an epoxy matrix. And so we were able to find the properties of the matrix using the equations given in the slides from last lecture. And you can see each matrix's Young's modulus, density, Poisson's ratio, as well as the strength parameter, stiffness parameter, and buckling parameter of each matrix. So the first 15 matrices are all for the epoxy. And then we found... Okay.
Okay, so the reason why you see like some highlighted like numbers over here is to basically single out like the top 5 fibers within the strength parameter, stiffness parameter, and buckling parameters. So within the epoxy matrix, these were the winners. So we have for strength-based, number 1, IISc carbon fiber. This one's important because it's literally number 1 for all strength-based, stiffness-based, and buckling-based composite fibers. Another one that came up frequently as well was another type of carbon fiber from a different company, UMT4612KEP carbon fiber, and that just like trailed behind like very slightly, but it's still very good. Another one that came up like again within all top 5 lists was the T700S carbon fiber. So all the carbon fibers are winning. Yeah. And I didn't do as much an analysis on, say, like, which ones were, like, the smallest. But if you can see over here, like, the different, like, boron nitride, like, silicon carbide, like, those types of kind of like glass-based, or even like even more like natural-based, like wool fiber, bamboo, basalt. Those tended to be lower on the list than what we found with the produced like carbon fibers on this list.
I'd like you to kind of check, because if I remember right, the company's nomenclature IM actually stands for intermediate modulus. So which means that they have various categories of low modulus LM, intermediate modulus IM, and high modulus HM. And so many of their HM fibers would be their own IM fibers. So especially for stiffness and the buckling based. So I'm not really convinced that the IM would be the winner amongst when the stiffness is involved, because the same company makes fibers which are higher modulus than that.
Okay. Yeah, no, I feel like we'd have to like look more into like the higher modulus and like the lower modulus and see like how that compares between those 3.
When talking only about carbon fibers, the density will not change too much.
Yes.
So it's mostly the stiffness which would change.
Yeah.
So if the HM, I don't know if I'm using the exact what they call, but it's something similar. So essentially, IM stands for intermediate modulus, and there's something for high modulus. So that might actually have higher values for the second two columns.
Okay, gotcha. All right, yeah, no, that'd definitely be something that we could check out for next class or something, you know.
It's good that you brought out a few natural fibers also.
Yeah.
There's also a lot of push towards greener composites, and it really helps to explore that. But you also showcase that comparatively they are still far.
Yeah. No, I feel
in
like,
terms of the
yeah.
performance.
Yeah.
So it's still a long way to go, but a good start.
Yeah, no, I'm sure if like there were modifications made, like these carbon fibers, they've been like modified and tested and developed to a point where they're able to be like the top of the class, you know? I feel like with natural-based fibers, if we did the same thing, you know, but like kept on modifying, kept on testing, you know, to try to see like what could make it better, you know, I feel like they could also become top of the class as well.
There's a lot of variables involved there in terms of how the particular fiber is grown. So the ground conditions of where it is grown, the soil conditions that is, and then the how you water it, the seasonal thing. So one of the issues that has been with natural composites is the widespread for the same fiber, like let's say take jute fiber or any particular fiber. So the spread would be much more in the variability because of the various conditions under which it is grown. So, but as you said, there's a lot that is being done already in terms of trying to kind of standardize them and have some way in which they could have kind of similar properties to what these have, at least in terms of the stability, if not in terms of, I'm not talking about the stability as buckling, but in terms of the range, in terms of the variations.
Yeah.
We want to have as small a standard deviation as possible. So we're heading towards that.
Okay, yeah, so I looked at a couple of the natural fibers that were on here, and I looked at some of the different studies that were put out, and a lot of them were not just natural fiber in epoxy, it was natural fiber in conjunction with something else, whether it was natural fiber and glass fiber, different types of natural fibers altogether, but it wasn't really common for them to test just the natural fiber in the epoxy. That's what I used for this one, which is why it performed so poorly, but if you combine it with something else, you can see the effects of the other material, bringing the strength and the buckling up. So, yeah, but then again, that's the other material that's doing the heavy lifting and not really the natural fiber. But if you're looking for something for specific applications where it doesn't need to be the strongest, doesn't need to be hold its shape the best, you can use a blend of natural fiber and synthetic fiber also.
So I guess you uploaded, you uploaded the source of the...
Yeah, they're at the end.
The whole like source list.
Yeah, we just made a list at the end of the slide, so you can click on any of them.
About how many fibers did you consider for each before you arrived at the top
15 for each.
So what are the major sources of information?
I mean, like from like what we saw online, a lot of sources of information came from like actual like research studies, like the like teams like testing out individual fibers and like seeing what the tensile strength is and whatnot. There were some also like material databases as well that we utilized. All of that can be seen within our sources though. So I don't know the specific names, but yeah. MATLAB? Okay, yeah.
And that's a good source because they keep updating it quite frequently. So you might get some latest information.
There was a lot of Science Direct articles.
Yeah.
About it. Like one would just lead into another one or cite another information about the fiber.
We're not done yet.
No, we're not. No. Okay, now we're on to aluminum composite fibers. So with this this one, it was kind of like the same thing. Like a lot of our aluminum and epoxy fibers, like there was some overlap between the materials that were used to like calculate the strength, stiffness, and buckling parameters. But within
You also look into the compatibility issue because I know all of these fibers will definitely work with epoxy, but with aluminum, do they?
Yeah, that's why for aluminum composite fibers, we use some, like, we didn't use some of the ones that were listed within, like, the epoxy for that specific reason. Like, they're, I found this, like, a pretty good source online. Where is it? Oh, yeah, like, specifically, like, talking about like what types of fibers would be good for aluminum matrices, and some of the most like more cited ones ended up being like the different like E-glass, S-glass, alumina, graphite, boron, silicon, like silicon carbon, Kevlar, titanium carbon. So those types tend to work better within, like, at least what I saw, like within the study that was provided with the aluminum mesh that they were testing. But yeah.
Yeah, glad you've done the due diligence.
Yeah. Yeah, so that's why we use that's why we tested like some of the fibers for like the aluminum while not using like some of the fibers that were tested for the epoxy. So over here you see like carbon fiber, glass fiber, Kevlar, more carbon fiber. It's a lot of glass and a lot of carbon fiber.
These have been, so these are just for the fiber, right?
Yes.
The Young's modulus and density that you have is good.
No, these are for the composite.
So
Yes.
you use the rule of mixtures to arrive at.
Yes. Yeah, Patrick can go more into like the actual process of how we calculated the things because he used like MATLAB code to, really, push things together. But within all of these, we found that graphite was actually one of the more top contenders when it came to.
It's kind of very generic.
Yeah.
Because there's so many graphite fibers.
Yeah, that's true.
So essentially, I think I mentioned in the class also that the difference between a carbon fiber and graphite fiber is just that it has more carbon content. The purity of carbon is more. So typically you tend to have better performance. But just like for carbon fiber, you're qualifying it by saying iron 6 or particular fiber. I think you need to make that qualification for graphite as well.
Okay. Yeah, no, I can look more into our sources to see like what type of graphite we used. But yeah, graphite unknown, and also like IM6 carbon fiber. Those two were also top contenders for the specific category, as well as again the T700S carbon fiber that came up a few times as well. And there's also like, especially around like 4 or 5, like that type of area, like glass fibers. Glass fibers also came out pretty strong as well. So, yeah.
The interesting thing is the liquid crystal fiber. Can you say something more about what actually it is?
Who searched up the liquid crystal?
So the liquid crystal fiber, I have the source like listed below, but I'm pretty sure what they did was they focused on the crystalline structure. I want to say it was like carbon, but it was like manufactured in a way to make it, good for like being used in composites. But as far as the actual like material, it's in the sources. I could.
It's liquid crystals are used quite frequently, as you know, for displays. So, but for structural applications like fibers, it's quite interesting to see, and because it's coming amongst the top fiber as well. So, we just want more.
No, should be Vectrin. This one up here.
Yeah, I think the first line kind of explains that. It's spun from crystal polymer. So essentially, it's the source before you get into the fiber form. What you start with, what we call as the precursor. So that matters a lot, even in carbon fibers. What precursor you start from. For example, there's something called the polyacrylonitrile. So based on whether you start from one kind or the other, you might end up with higher stiffness or higher strength. So it's very important to be aware of that. So it's interesting that it's essentially being spun out. It's something like how the spider kind of spins out the web. So it essentially has a liquid gel that once it is exposed to the atmosphere, kind of solidifies. So though it's liquid originally or semi-solid, so essentially it turns out that way. So just like we were talking about agricultural fibers or natural fibers, there are a lot of animal-based fibers as well. So for example, silk fabric is something that is known to have fairly large strength and stiffness against silks. So there's a lot of work that is being done towards how you can go to what are known as technical fabrics or technical textiles. So other than for human clothing, actually applications for engineering. So there's a little more that needs to be done towards that, and there's a lot of work being done towards animal-based fibers as well.
I can talk about the MATLAB. So after a while of like computing some of the values, I figured it would probably be easier just to, write code to do that for me. So here's an example for like T700S. I wrote a function called properties, and you input the Young's modulus, the density, Poisson's ratio, tensile strength, and then the type of matrix, whether epoxy or aluminum. And then you get the matrix, Young's modulus, the matrix density, Poisson's ratio, as well as the strength, stiffness, and
many
buckling.
Many sources might have different unit systems, right? So you ensure how it would.
Yeah, I made sure that the units beforehand, like before inputting, were.
That before you.
Yeah.
So that's also probably something that you can build in if you want to longer run for other purposes as well.
Yeah.
So you can build in the unit system as well, so that you can have all the conversions automatically taken care of, save you a lot of time.
Yeah. I mean, the more I thought about it, I wasn't intending the code to be as like deep as it was or as long, but like the more I thought about it, I did think about like, I don't know, maybe like also putting in the values into a like Excel matrix and just like having it spit out a new one, but
because there's no standardization across the industry in terms of what units to follow. Each company follows its own units. They might give multiple unit systems as well, because some customers are maybe coming in from different countries and they may be more familiar with certain unit systems.
Yeah, and on the matrices, we try to be consistent. So the tensile strength we did mechanisms with the shear modulus with gigapascals, and a lot of the data was put to but it was just an easy conversion to put that in the
yeah. So we use this for a lot of the different fibers. We had like the fiberglasses, the aramid fibers, and then in the next slide, we have the start of the code.
And another thing is, since we're getting into coding, probably a way of automatically extracting from databases. Like for example, MacWeb is a database.
Yeah.
So instead of you manually searching for fibers, it may or may not always lead to the optimum.
Yeah.
It might be one of the higher performing fibers, but may or may not be the highest. So it's always good to do an automatic search over a database if that's possible. For example, if you can kind of output an Excel sheet out of the MATLAB information or data, then you could probably have your MATLAB code reading that to spit out your top file.
Yeah. So yeah, once again, I wasn't intending it to be as long, but like what I started out with was just creating functions that would find the value for like each matrix property. So like here, this finds the matrix Young's modulus. And so we have our constant values for like each matrix, like the epoxy and the aluminum. And then we use the formula where we basically take the volumetric fraction of each part of the composite's properties, and then we use that to find the property of the total matrix. So the one above did the Young's modulus. This is for the Poisson's ratio. This is for density. And it's pretty much the same process, although the equations are slightly different for some of them. And then at the very end, I just decided to like combine all the functions into one and use like the above functions as like helper functions, so that you put in all the values of the fiber, and then it outputs all the values of the matrix as well as the performance parameters. And then our sources.
So let's revisit some of the things that we've been doing in terms of the assumptions. So we started off with elastic, material linearity, then no body moment distribution, and I think the next thing was existence of a strain energy density, and we brought in orthotropy and transverse isotropy. So that's where we were last time. So we said that all of these can be all of these can be kind of independent of each other, but we wanted to put them all together, build them up so that we can get to something that is more practically applicable to a lot of problems that you would like to work on. So we would soon be completing this slide, because we have two classes today. We will see that there is something very interesting that will come out most probably in the afternoon session, and I really want all of your total attention towards it, because what I'll be presenting once these assumptions are done and we get to what we are going to be presenting in today's afternoon class, we will see that this pretty much we have completed the course. So in terms of what is the takeaway from this course, if you want to have just one takeaway, it would be probably what we will be doing this afternoon. If hopefully I'll do things a little fast so that I can get there, but otherwise maybe in the first class of the next Thursday. So now the reason why that is so important is that it will kind of give you the big picture of structural analysis, how all of structural analysis is done, and then we will bucket all different simple problems the way structural analysis is typically taught. So where we look at topics almost as if they were kind of independent of each other. So you had an issue with that? Yeah. Okay. Yeah, you can switch it off and on. Yeah, but the recording is still on, right? Yeah. So what we would have is, instead of going as topics which are kind of disconnected from each other, we will build up a big picture where we will see where each of the topics that we are going to be looking at in the remaining 8 or 9 classes will all fall into that big picture. So if you understand this big picture, it's kind of, you understood everything else. It just becomes like examples of that big picture. So which is why I'd like you to really focus on this, because this is not the way in which this is taught, leave alone for undergrads, even for masters or PhDs. This is typically not the way this is taught. So this has been of great pedagogic value throughout my career. I've seen a lot of students have benefited from this and who have gone on to become professors themselves around the world. Many of them have told me that this kind of completely changed the way they thought about structures, and therefore it kind of helps. And this is something probably best introduced at the undergraduate level, rather than wait for people to get into a master's or PhD and make them unlearn a lot of things that they have learned and then try to bring this in. So which is why I thought it's going to be of great significance. 1 minute. Yeah, significance for you all over here. So now let me just summarize, instead of going one by one, which we already did earlier. The end result of all of this we saw at the end of the previous class was in the form of sigma. So we saw that it's in the form of a matrix equation, which involved 6 by 1 column matrix given by a 6 by 6 matrix, which is purely material properties, multiplied by your gamma, which was 6 by 1, again the 3D strain. We said that stress and strain are actually second order tensors, and therefore this particular notation, which is a kind of a compact notation, is not mathematically rigorous. But nonetheless, it's very convenient to use. And it's called as the Voigt notation, named after a person who was involved in representing it in this particular way. So it's called as the Voigt notation, and this is something that is very commonly used in all books, and which is what we will stick on to as well. Now this is one way of writing the stresses in terms of the strains, and this is very useful when you're doing like what Patrick did in terms of a MATLAB code or something you're coding. This is very convenient way, but most experimentalists prefer the inverse of this particular equation. So in other words, you have a gamma 6 by 1 given by a flexibility matrix, which is 6 by 6, which is multiplying your sigma, which is your 6 by 1 again, and this S of course has to be the inverse of your C matrix. The 6 by 6 matrix has to be inverted in order to obtain this. Now while this is very useful, this particular form Both are void notation, of course, because you are representing what should actually be a 3 by 3 matrix as a 6 by 1. So essentially, because it's symmetric, you're taking advantage of putting the diagonal terms and the off diagonal terms one below each other, and that's how the void notation comes up. So as I said, this particular form of the void notation equation, giving the strength in terms of the the stiffness, the stress in terms of the strain, is essentially useful for more useful for computational purposes. Whereas this particular form of the equation is more useful for experimental purposes. And we'll see exactly why if we can kind of expand this equation out, very similar to the way we were writing the whole thing in an expanded form for the top equation. So it involves the 3 normal strains to start with, and then the 3 shear strains, 2 gamma 2 3, 2 gamma 3 1, and 2 gamma 1 2. Okay. While the order of the first 3 is easy to remember because it's 1 followed by 2 and 3, the last 3 sometimes people get confused and they kind of interchange, but the standard notation is to or a mnemonic to remember this is that the first one misses a 1, the second one misses a 2, and the third one misses a 3. So that way you can very easily remember. It doesn't matter if you interchange, because if you put 3 2 or 1 3 or 2 1, because we know by definition these strains are symmetric, so it really doesn't matter if you kind of interchange, because essentially the change in the right angle between the x2 and x3 direction, so whether it's between x2 and x3 or x3 and x2, doesn't matter, it's the same change in angle that you would essentially get. And remember the factor of 2 for all these shear strains, because gamma by itself is a tensorial shear strain, whereas once you put the 2, you're getting the engineering strains, which are the same as far as normals are concerned, but only in the case of shear there's this factor of 2 that you need to account for. So it's only when you remove this factor of 2 that a lot of the standard tensorial manipulations that you can do with second order tensors will be applicable, whereas purely from a direct experimental measurement it's always easier to calculate a change in right angle, and therefore this is something that is used in engineering, and which is why it's called an engineering shear strain, right? So now, based on all of these assumptions, we had a simplicity in as far as the S matrix is concerned, and very interestingly, this is compliance. This S matrix is called compliance, which is the inverse, of course, of the stiffness matrix. This is called the stiffness. I don't know how it started, but if you look at it, it's actually the other way around. C for stiffness and S for compliance. Okay, so but that's the standard notation that's used in a lot of books and literature. So we will continue to use that as well. Right. So remember that. So now we can, whatever simplifications we did with the C matrix, the same thing is valid for the S matrix. Remember that the C matrix was of the form instead of a fully populated 6 by 6, based on some of the assumptions that we made over here, we saw that it turned out to be the first 3 by 3 was fully populated, and then the remaining 3 rows and columns had only a diagonal term. So it just had terms. So when you invert the matrix, it will be the same, because when you invert a 6 by 6 matrix, it's much more difficult. Even with MATLAB, it will take a little more time compared to inverting a 3 by 3 matrix, which is what we will take advantage of. So that when you are inverting a 6 by 6 matrix, of which the 4th, 5th and 6th rows and columns have only a diagonal term, then all that you need to do to invert them is to just take the reciprocal. Whereas the first 3 by 3, you can invert a 3 by 3 matrix much more easily than a 6 by 6 matrix, and which is essentially how you end up with this. So the form in terms of which are non-zero and which are zeros, whether it is C or S, it would be the same. So just that the, of course, the units would become just the reverse or reciprocals of whatever units you are starting with, etc., because it's the inverse matrix that you have. So let's just fully populate that so that I can explain to you why this difference, that in one case it's easier for experiments, the other case it's easier with computations. So that argument will become clear once we write this out. So here you have your stresses, the same order, the normal stresses going in first, and then the shear stresses, either using sigma itself, or this is another notation which is commonly used, tau, for the shear stress, just to distinguish that the stress kind is different. That one case it is normal, the other case it is shear. This we will see a lot when we work on shear forces in beams, transverse loads in the beams, that is forces causing shear stress distributions. We will also see this once again when we visit torsion, because when we have torsion, we will see that the effect of that in terms of how the structure reacts to it is essentially in the form of a shear stress developing. That's the way it automatically does that, right? So now, so going to this, we have, of course, a symmetric matrix, and the diagonal terms are going to be S, the compliance. So you have S11, S22, S33, S44, S55, and S66. And here you have the Poisson's effects, S12, S13, and S23. Okay, and all of these are essentially zeros, right? So, which is what I was saying, instead of having to invert a 6 by 6 matrix, which will be much more complicated, all you need to do is take the reciprocals of these, because that's the only term present in those rows and columns. It just becomes 1 by C44, this becomes 1 by C55, and this becomes 1 by C66. Whereas all you need to do is to invert this fully populated 3 by 3 matrix from C matrix, C11 to C33, whatever you had, you invert that to get these values of the S matrices, right? Elements of the S matrix. Now, why is this better for experimental work? See, essentially, it's in terms of how you can apply the boundary conditions when you perform an experiment. So, for example, if I'm performing an experiment of a tensile load in a UTM, universal testing machine, I apply a tensile load along the length of this particular specimen. I can measure the strains by using strain gauges. So, I put a strain gauge parallel to the loading direction. I put another strain gauge perpendicular to the loading direction this way. I put another strain gauge perpendicular to the loading direction this way. So then I can start increasing my load. As I increase my load, I know the load divided by the test section area is going to be the stress in that, and for that stress you're measuring all the strains. So what exactly are we doing from this matrix equation point of view is this experiment that I just described to you. I'm keeping only sigma 11 as non-zero. I'm not keeping all these edges as free, which means there's no stress on them, right? So in other words, your sigma 22 is 0, sigma 33 is 0. I'm not applying any shear stresses as well. And therefore, all the readings that I get will help me populate this first column, because remember, with only the first element of the 6 by 1 being non-zero, it's going to, in the matrix multiplication, you know that is going to multiply the first column of the compliance matrix, and therefore we already know that the 4th, 5th and 6th are zeros, but we need the 1st, 2nd and 3rd, and that is very easy to just read out of the strain gauges parallel to the x1 direction and perpendicular, which is the x2 and the x3 direction. So once I read that, all that I will be doing is to plot my input, let's say, as sigma 11, and this is let's say the gammas, which is gamma II, and then I get essentially curves like this for 1, 1, 2, 2 and 3, 3. But once we have transverse isotropy, the 2 and the 3 directions would be same, as the properties would be same. So in other words, essentially I'll be getting readings from the strain gauge at various values of the stress. So remember that this curve is usually plotted the other way around. Remember, sigma versus gamma. Stress strain curve, usually you plot it the other way around. So in other words, the slope of this is not the Young's modulus, but the reciprocal of the Young's modulus. So in other words, if this is for gamma 1, 1, in other words, your eyes are taking on the value 1 each. So then here these are your gamma 2, 2 or gamma 3, 3. And the 1, 1 we will also call as the direction along the fiber. So this longitudinal direction. So we can also refer to it as LL, right? So similarly, these we will refer to as gamma TT. And 3 is also a transverse direction, because essentially anything perpendicular to the fiber, whichever direction you take is the transverse direction. So I can call it either as gamma TT, and to just distinguish 2, 2 and 3, 3 directions, the x2 and x3 directions, I can call the other one as T prime. So that I can call gamma 3, 3 as gamma T prime, T prime. The value is the same, just that I want to keep the direction as part of my workload. So that's the reason why I call one as TT, other as T prime, T prime. Essentially, x2 is T2 direction, T direction, and x3 is the T prime direction. Both are transverse directions, and it really doesn't matter if you interchange them or you rotate them as well. Within that plane of transverse isotropy, it remains one and the same. But that's what transverse isotropy means, right? So now, so based on all those points that you get at different loading conditions, you're just drawing a straight line through them, and then the slope of that line in the top curve over here, sorry, it should be the other way around, because usually you'll magnitude of the strains will be much lesser for the longitudinal direction, where the stress stiffness is much more. So let me interchange these two. So this is essentially for this, and this is for this particular curve, right? So now if you look at gamma 1, 1 plot versus sigma 1, 1, you see that the slope of that is going to be 1 divided by EL, which is the longitudinal modulus that you have used, for example, in your home assignment as well. The longitudinal modulus of the composite that you calculated based on the fiber and the matrix properties is essentially that 1 by L, whereas the slope of this is given by 1 by ET, where the transverse modulus is involved, and ET is typically much smaller compared to EL. In fact, we saw examples of certain fibers where we looked at the ratio of these, and we saw that, for example, if you look at the EL divided by ET for carbon fibers, it could be of the order of 14. So as order of magnitude difference usually, but in some fibers like typically the metal matrix composites that you dealt with, you would see that EL by T is still greater than 1, but not so much greater than 1 that you can call it very less than. It is typically less than. So so this is true with most polymer matrix composites, whereas for many other composites you would see that ET is just less than EL, not very much less than EL. For example, the homework assignment that you had with the aluminum matrix composite, which is a metal matrix composite, okay, you typically abbreviated as MMC, right? So now the utility of this whole thing is that now, because the way the experiment is performed, I am applying a load in one direction, I am keeping all the other edges free, so automatically the stresses are 0 on these other directions, that is gamma 2, 2 and gamma 3, 3 are automatically 0. So only gamma 1, 1 is present, sorry, only sigma 1, 1 is present, all the other sigmas are equal to 0, and therefore I have an easy way of populating the first column of this matrix. So this particular experiment, where all that I did was to take a particular specimen you typically have a dog bone kind of specimen over here, and this is the test section. Its area is what is going to divide the load by the force that you're going to apply, and this is your x1 direction and also the load direction. So your P by A is going to give you your sigma 11 or sigma LL, and now the strain gauges that are put on this in this direction, also another strain gauge in this direction, and maybe in the third direction as well, if you'd just like to cross verify if it's really transverse isotropic or not, but otherwise that is not needed, because anyway those two are going to give you the same curve, so just 2 strain gauges would suffice. And just by plotting that and taking the slope of that, I will be able to get my S11 and S12. So those two values, and S12 is same as S13, and therefore I have got my entire first column because the others are zeros. Okay, so such a simple experiment to perform. Now suppose I wanted to perform an experiment in which I want to directly calculate C instead of S, that is the stiffness instead of the compliance. What do I have to do? I will have, of course, this gammas on the right hand side, the sigmas will be on the left hand side. So I have to perform an experiment in which I set only gamma 11 to be non-zero to start with, and put all the other gammas equal to 0. Now imagine, how do you achieve that experimentally? You want to once again create a certain gamma 11 which is non-zero, but you have to ensure that the gamma 22 and gamma 33 are equal to 0. How do you ensure gamma 22 and gamma 33 are equal to 0? But the material, remember, has a non-zero Poisson's ratio, and because of which once I try to pull it this way, it's going to contract in the other two typically. So if I want that to remain 0, I have to ensure that I try to keep this also pulled apart in such a way that it will not change the length, which is, if not impossible, it's a very difficult experiment to do. So which is why you will see that typically it is this which is first got, and then of course you can invert that to get your C, and then you start using that C for the computational purposes, which is all that you would see over here, right? So your S11 turns out to be your 1 by EL, and similarly your S12 is your minus nu LT divided by ET, and S13 is also the same. So both S12 and S13, because both are SLT or SLT prime, will turn out to be this, and this is the Poisson's ratio definition that you showcased in your homework as well, and that's how this is kind of typically populated. So very easily you can see that this whole thing can. So how did I get the second column? Because this, I know this matrix is symmetric, so I got this S21, and therefore I am just putting S21 over there as S12. So that's how I am getting that. Otherwise I have not performed an experiment where I put just sigma 22 and keep all the others 0. In other words, I apply only a transverse direction load and stress, and keep the other directions equal to, other stresses equal to 0. So then I can populate my second column, but that of course I will need to calculate S22, because I don't know S22 as yet. So what I know is S12 as a whole, I don't know the numerator and denominator separately. To get the denominator and therefore to get nu LT, I have to perform another experiment where now I create a specimen such that in this particular specimen all the fibers were parallel to the load. I will create another specimen in which I will have all the fibers perpendicular to the length of the specimen, and now I will again put this in the UTM to get an uniaxial load. So now the fibers are running this way, so what I am measuring is actually gamma 22. So I am applying a sigma 22 and measuring gamma 22, keeping all the other stresses equal to 0, and which very easily gives me this S22. If I get plot the same thing, instead of I equal to 1, which is what we did over here, we will be plotting I equal to 2 and versus sigma 22, and that curve that I get, its slope will be equal to 1 by ET. Right, the transverse modulus. And there's a reason why the symbol E is used over here. Even though we are talking of matrix S, we use mostly E's here because this is our engineering. So you're engineering in the sense that you're actually performing an experiment in order to determine these things, and you're experimentally populating based on the slopes of the curves that you get out of that experimental result. You're ending up with this particular matrix that you have over here, and therefore these are called as engineering constants, whether it is EL, ET, nu LT, etc. These are all called as engineering constants. Are there any doubts about this so far? Okay, so you can stop me whenever you want, and if you have any questions you can ask me. So then once you have done this, you don't need to do S33 separately, because you know that the 2 and 3 directions behave very similarly to each other, and therefore your S22 and your S33 are equal to each other, both are equal to 1 by ET. The other case we had called it 1 by ET prime, but whether it is T or T prime doesn't matter. It's only to distinguish for our own convenience, X2 and X3 we are calling it as T and T prime, but the values are one and the same, and therefore you have 1 by ET and 1 by ET prime equal to each other, right? So this is equal in turn to 1 by ET prime, which is equal to your S33, right? So now similarly you would have got your S13 and S23 as well once you have a load in the third direction, which is also the transverse direction. So here itself I could have performed the same experiment that I am doing here. Instead of having just one strain gauge, which would have helped me get ET, to get the Poisson's ratios, corresponding Poisson's ratios in the other direction, I would have to put a strain gauge which is perpendicular to that and measure that. I would once again plot that over here, and I would be getting, because that strain gauge, remember, is measuring strain along the fiber direction, because this is along the fiber direction. So that's actually measuring a sigma 11. So one experiment at a time, applying only one of the normal stresses, keeping the other normal stresses and shear stresses equal to 0. Shear stresses, whether you keep them 0 or not, doesn't matter in the principal material directions, because anyway they're decoupled. All these are zeros, so the shear is decoupled already from the normal. The only things which are still coupled is the normal with other direction normals. So normals in two different orthogonal directions are essentially coupled because of the Poisson's ratio. So all you need is, and since you have transverse isotropy, you typically need only 2 strain gauges at a time. The third strain gauge will be redundant. It's only probably you can use for verification or validation, but essentially it's going to be one and the same result that you're going to get, and it's just 2 curves like what we saw over here, and each of them is going to help you get your EL, ET, nu LT, etc. And then finally this S23 is something that is coupling, remember, a T and a T prime. So in other words, I'm applying a load perpendicular to the fiber, creating a stress perpendicular to the fiber, and I'm measuring in a direction which is orthogonal to that what is the normal strain, and taking the ratio and the negative of that, which is your Poisson's ratio in the other direction. That will help me get my S23. Once again, from the plots, essentially the ratios, the slopes, and then the ratios, and then you end up with your populating your S23 as well. So now I think it would have become very clear why I said that C is more convenient with computational and S is more convenient to deal with in an experimental work. And this is almost always the stiffnesses and or compliances are determined experimentally. It's very difficult to do a material science model and try to get to the values of the these from purely from, let's say, the crystalline structure or any other microstructure that you have for the material based on that. That's typically in the realm of material science. It's not that it's not done, it's done by them, but it's kind of very rare and typically done for newer materials that are developed, but mostly it's based on experiments, because that's how you get the S matrix purely from experiments, and then you invert that to get C matrix. So essentially the source of that also is the experiment that you have already done to get this. You're just inverting that to get your C, and which then you start using in your computations. So typically most material properties, not only stiffnesses but even the strength, the same test, I can go on increasing my P up to the limit where this actually gives up and therefore breaks. So from that I have not only got my EL, but I also have my sigma U in the L direction, that is the longitudinal tensile strength I would have got. Similarly here I would have got the transverse tensile strength with this particular experiment over here, right? Now, so I think that kind of explains this whole thing. And in the end of previous class I was talking to you about the effects of this particular assumption, transverse isotropy, which is a fairly valid assumption, because anything perpendicular to the fiber, whichever direction, really doesn't matter, the properties are going to be the same, and therefore, which is the reason why we have that in the green font rather than an yellow or a red font. But soon we will get into realms where we are not happy with those assumptions. We'll be using a red font to showcase that, but that's how it's typically done, and therefore we have to introduce that to understand a lot of the literature that is already present. It's very good for first cut rough analysis, but for most aerospace grade analysis now that's kind of being given up, but nonetheless, because it is a legacy that we have got, traditionally that's been done that way, so we just will revisit that so that you'll be familiar with literature associated with that as well, right? Now I think this is kind of clear. Any questions or doubts on this? Fine? Yeah. Let's move on. Oh yeah, one more thing before we leave transverse isotropy is that transverse isotropy, where we had said, let me use, so whether I do this exercise with the S matrix or C matrix, it's one and the same, doesn't matter. So last class we did it with the C matrix. Okay. So now we have, what we were saying is that S2, S1 3 and S2 3, the rest are zeros, right? So now remember that the 5 5 and 6 6, what they are related to is your tau 2 3 and tau 3 1, and whether you say tau 3 1 or tau 1 3 doesn't matter, because there are no body moments, they are equal to each other. So in both of them you would have 3 as one of the common subscripts, and the other subscript is essentially going to be either 1 or 2, right? So similarly you would see that, sorry, tau 3 1 and tau 1 2. So in these cases, if I see that, it's essentially LT or LT prime, okay? So both are of a similar quality as far as this is concerned, which is why these two are equal to each other, because essentially it's the shear stress which is associated with that, which is your 1 by GLT, okay? Because it doesn't matter whether we write LT or LT prime, which is what P and T prime stand for 2 and 3 direction, L stands for the 1 direction, that's our convention. So you see that GLT and GLT prime are one and the same. So the experiment that we perform, where we keep only either one of these as non-zero and try to get the strains measured, there is a way in which we measure the change in the right angle by an appropriate arrangement of the strain gauges. So essentially, when you take that plot and take the slope of that, you will end up with 1 divided by the shear modulus in the LT plane. So that's So there's no need to do a separate experiment for tau 31 and for tau 12, just like there was no need for a separate experiment for sigma 22 and sigma 33. Both are transverse directions, so one of them, if you perform, you can populate the other as well, which is why we had already said that S22 and S33 are equal to each other. They are equal to 1 by ET, and which is of course equal to 1 by ET prime as well. So S22 equal to S33 is one thing we have got. S55 equal to S66, because both are in the LT plane or the LT prime plane, which is essentially one and the same as far as material properties are concerned. And then we also said that here again 2 and 3 can be interchanged. One is T, the other is T prime. Both are transverse. One of course is longitudinal. So which is why we had one more equation over here, that S12 is equal to S13, right? So how many equations do we have already? This is one equation here, this is a second equation here, and there is a third equation over here. Up to this point, when we had made these assumptions, the first 5, before we went into transverse isotropy, we said that all of this put together, the 5 assumptions, was leading to 9 independent constants, and that's also very easy to see from your matrix, because there are 6 diagonal terms and 3 off diagonal terms. So 6 plus 3 is 9. So and of course there are 12 non-zero, because this is because of the symmetry of this matrix, you will have non-zero terms here as well. So this is 6 plus 3 plus 3, totally 12, but only 9 of them are independent. If I know these 9, I can get the other 3 as well. Anyway, the rest are zeros, right? So up to 5 itself we had reduced. Remember, we had started off with material linearity as 81 constants. At the end of this it was 81. Here it was not even constants, they were all nonlinear functions. So this was nonlinear functions. Then we started with 81 constants over there. Then we went to no body moment, so we reduced the stress and strain to the void notation. So we got 36 constants over there. Then we came to strain energy densities existence, so that matrix 6 by 6 was symmetric, so we needed only 6 diagonal terms and 15 off diagonal terms, a total of 21. So the number of independent terms has been reduced from 81 to 36 to 21 to 9. We already saw in the previous class. Now we want to see what all transverse isotropy does for us, so that further reduction from 9 to the number of independent constants comes down, right? Already we have 3 equations, because one S12 equal to S13, the other is S22 equal to S33, and here S55 equal to S66, okay? This is because both of these are 1 by ET. This is because these are both involving a new LT divided by ET, and this is because there is a 1 by GLT, right? So that those 3 are kind of clear. The third one, which is not kind of clear, will actually be part of your next homework, and that homework is essentially to see that there is a relationship between your S44 and your S22 and your S23, okay? And these 3 are not independent, they are kind of related to each other, okay? So I'm not putting an equal to sign over there, but I'm just keeping that this way. And the same thing holds in your C matrix, that C22, C23 and C44 are related to each other, and in fact the expression is much simpler over there, that you can write your C44 as C22 minus C23 divided by 2, okay? So already we had 3 equations, one because S22 equal to S33, one because S55 equal to S66, and another because S12 equal to S13. Now we have one more relation relating the C's. Of course you can get the inverse form of that to relate these 3 quantities over here, but the moot point is that you have a 4th equation as well. So not only 3 that we have already shown in the matrix itself through these equal signs and the equation numbers that I wrote, equation number 1, equation number 2 and equation number 3. Now this is equation number 4, okay? So with these 4 equations you can see that your 9 independent coefficients is going to become 9 minus 4, which is equal to 5 independent constants. Okay, and this is, remember, still we are in the 3D. So in other words, we are looking at a general 3D model, 3D structure. We have not kind of reduced it to a beam or a shell or any kind of, this is at the material level. So all these are material properties. In other words, even if I change the size of this specimen and try to do the same experiment using the same things, you'll get roundabout approximately the same values. There will be very, very slight variations because of the standardization or non-standardization that is there. But essentially it's a material property, so it should end up giving you the same results, which is why though the tests are done with an ASTM standard kind of specimen, you're not having only an aircraft built out of ASTM specimens, right? It's based on aerodynamic efficiency and other things. You're designing the aircraft structure, but since you're using the same material, whatever properties I got out of these experiments with that same material, I'm going to use for that material as far as the aircraft structural components are concerned. In other words, it's expected to behave the same way, even though it doesn't have the same shape and size as these specimens. This is just to for a ballpark in terms of agreeing experiment across experiment. So some kind of standardization is done. So typically what are known as the ASTM standards are typically used for that, but nonetheless that is just to perform these experiments, to get these points, to join those points, get the straight lines, get their slopes, and use their slopes to populate this matrix, invert them to get your C matrix, and that's all that you have. So therefore these 5 independent constants that are there can all be listed out now in terms of your engineering constants. So what are they? Of course there's no one way of doing it, because given any set of 5 independent ones, the 6th one can be determined. Which 5 you choose for your basket is up to you, but typically what is used in the literature is one is which are these 5 independent constants. We are listing it out, right? So one is your EL, the longitudinal modulus, which is along the fiber direction. The other is ET. Then there is a Poisson's ratio nu LT, all of which we could get by just that single experiment that we were doing in 2 different directions. So we were able to get all of that. Now as far as the shear is concerned, when we are trying to do this, typically what is done is a torsion test is done. So a torsion specimen is used, and because torsion is going to result in shear stress and shear strain, we plot them and eventually we get the slope of those curves, and that helps us to get our GLT, right? So GLT is another independent quantity, and then you have a 5th one, which can either be, in some cases you can take it to be your nu TT prime, or in some other cases equivalently, or GTT prime. The reason is these two are related to each other, and that is essentially coming from this, and this is very similar to, if you I don't know if you are familiar with this particular equation relating the shear modulus and the Young's modulus of an isotropic material. For isotropic materials, the properties are the same in all directions, so you don't need to put subscripts for your new Poisson's ratio or for G or for E. All of these subscripts that we had to put there are because properties are different in different directions. They're no longer isotropic, what we call as anisotropic. In fact, special case of that anisotropy is orthotropy and transverse isotropy, which is all that we used, and then therefore we got all these subscripts. But this is for an isotropic material, a fully isotropic, in the sense it's a 3-dimensional isotropy, not only transverse isotropy. Okay, so then you have this particular equation between the shear modulus, the Poisson's ratio, and the Young's modulus. In other words, you don't need to do 3 separate experiments to determine each one of them. If you get any 2 of them, you can get the 3rd directly by using this particular equation. Now this particular equation, because it is valid based on isotropy, that iso is what we are considering over here, but just that it's not 3D isotropy, but just an isotropy in one plane. So that particular plane, what is the G? That G is GTT prime, because that plane is perpendicular to the L direction, and that's where we introduce these two coordinates x2 and x3, or xt and xt prime, which is therefore the shear modulus in that particular thing. So instead of G, we have now, when we go from fully 3D isotropy to transverse isotropy, then we do need to introduce subscripts, but there is a equality that is getting expressed now, and that's essentially in terms of your ET divided by 2 into 1 plus nu TT prime, and therefore you see that there is a correlation between ET GTT prime and nu TT prime. Okay, so it's the same thing, same equation, G equal to E by 2 into 1 plus nu, but now expressed in this. Now, those of you who are not familiar with this particular derivation, you'll see that in a lot of textbooks. So I want you to, as part of your homework, go look at this, how this is derived, and based on that, I want you to take this up as the first part of today's homework, where you are going to prove that C44 is equal to C22 minus C23 by 2, which is just another way of saying the same equation. Okay, so if you can rearrange these terms to see what C's are in terms of S, and you already know what S is in terms of the engineering constants, you will end up with that. But in order to get to this, first of all, you need to know how this was derived for an isotropic material, and therefore based on this particular thing, you can try to use the same way you can derive this particular equation. Then you can substitute this to get the S, and you can substitute the S to get your C, and then you can show that the relationship between C44, C22 and C23 is fairly straightforward and simple like this. So this, which is what I want you to prove. Okay, is the homework clear? I will explain it, and I will anyway be sharing the slides as well, so you will see that described in the slide as we go forward, so you don't need to kind of note it down. So now we have this, so we have 5 constants, which is what I was trying to explain to you, from 9, so 81 to 36 to 21 to 9 to now 5, and those are the 5 that we have: EL, E2, ET, nu LT, GLT, and either one of these, because if one is given, the other can be calculated using this particular equation, because already ET is known, right? So you have only 5 independent constants that you need to deal with. Even when you're having an arbitrary 3-dimensional loading, it's neither necessary for it to be a beam nor a shell. It could be any arbitrary shape. It's purely material properties is what we are looking at. It's not geometric property, and this can be obtained. In other words, a material is fully understood at least up to the point of failure if you know these 5 constants. Now we are not satisfied in terms of simplifying it. We want to make more assumptions, and that's where we get into kind of dicey territory, where we make certain assumptions which are kind of not valid, and the first one of them is something that you probably have heard. How many of you heard of this assumption, plane stress? No? Okay. So let's explain what that is. Very simple. From the very name, you can see that all of these stresses are within a plane. Just like we were talking of transverse isotropy, what did it mean? It's just that perpendicular to the fiber direction is the transverse plane. That was isotropic, all properties in that were the same. Now we are making an entirely independent, different assumption over here. Whether we have made those assumptions or not doesn't matter. This is a separate assumption that a lot of people make in a lot of problems, and that's essentially your plane stress state. So let me explain to you on the board what that means. So that's the 7th assumption, right? And this is when we start getting into plates to start with, and then we will get into beams as well. Okay. So now we know that in the void notation we had the 6 stress components, which is your 3 normal ones, sigma 11, sigma 22, sigma 33, sigma 23, or call it tau 23. Right. So now let's say without loss of generality, when we say plane stress, we can choose that plane in which we introduce the coordinates x1 and x2. Okay. So that plane in which you're talking of it to be plane stress, we will call that plane, or in that plane, whichever plane that plane stress is in, we will call that, we will introduce the coordinate system x1, x2 in that plane, so that x3 is perpendicular to that specific plane. So it's up to us how we go about introducing that. Now forget all the things that we talked about in terms of 1, 2 and 3 as far as the first 6 assumptions are concerned, x1, x2, x3. That's a different thing, where we were looking at x1 to be fiber direction, x2 and x3 to be perpendicular to fiber direction, etc. Because this plane stress state you need to understand irrespective of whether we are dealing with composites or not, and this is a common thing which is made with a lot of metallic structures as well. So you need to understand it purely from that point of view. Then we will try to link those two together and come up with all the 7 what actually happens. Now what is the advantage of getting to plane stress? Already we have started with 9 terms becoming 6 because of the symmetry of the stress matrix, because of the absence of body moment distribution, right? So that we had only 3 shears instead of 6 shear stresses that we actually started off with. We will have only these 3. Now we want to reduce this further. So what do we do over here? We assume this plane stress approximation, and we introduce within that plane a coordinate system x1 and x2 orthogonal to each other, and then we say all the stresses are only in that plane, which is what plane stress means. So all non-zero stresses are within that plane. Any stress which is perpendicular to this particular plane is actually 0. So this plane which is, or the direction which is normal to the x1 x2 plane is of course x3, right? So normal to the x1 x2 plane is your x3 coordinate. So anything which is along the x3 direction, those stresses are equal to 0. For this we need to kind of understand how we define these stresses and how the subscripts are there. So this you might know, it's just kind of a short review. So essentially if you have, let's say, a structure like this, and you have introduced, let's say, an x1 along this direction, and let's say you have introduced x2 along this direction. So that's the x1 x2 plane in which I want x1 x2 plane in which I want to have all my stresses. Okay, so that x1 x2 plane has something which is perpendicular to that. For a dextral triad, b1 cross b2 should be along b3, so therefore your x3 has to be downwards, right? So now what I'm saying is that on the x3 face, all the stresses that will be associated will have the first subscript as 3, right? So in other words, there will be a normal, if I take a over here, there could be a normal stress which is acting over there, which is on the 3 plane because x3 is perpendicular to that, and in the 3 direction, and therefore we call that as sigma 3, 3. So this is the nomenclature generally for any sigma ij. I stands for the normal to the plane on which that stress is acting, and J is the direction in which the forces are acting on that small infinitesimal area, and eventually you shrink that area in the limit to go to 0 to get your stress definition. Force by area, but as the area shrinks to 0. So that's essentially your sigma 33. Why is it 33? The first 3 refers to the fact that the normal direction is the x3 direction, and the second 3 refers to the fact that the forces acting on that infinitesimal area are also in the 3 direction, therefore it is sigma 33. Now we are saying that all the stresses have to be in the x1 x2 plane, which means that those stresses which are non-zero are sigma 11, which is going to be stretching this plate in the x1 direction. It's going to be sigma 22, which is going to be stretching the same plate in the x2 direction, okay, stretching or compressing, in which case of course compressing it becomes negative, and then a shear that can act on this, right, which is your tau 12, which is what is known as the in-plane normal stresses. That's your sigma 11, sigma 22. Okay, once again I insist, don't get confused with one being the longitudinal or fiber direction and 2 being the transverse or the perpendicular to fiber direction. That notation is different, this notation is different. The fibers can be in any direction over here, doesn't matter. Here we are talking of the structural shape. So far we are primarily talking about the material itself and the geometry within the microstructure of the material. Now we are talking of an actual structural element, which could be, let's say, a panel of the wing. So for example, on the top surface there will be many panels of the wing. So this, you can think of this as one of those panels, either on the top surface or bottom surface. Similarly, it could be on the fuselage. It might have a slight curvature as well, doesn't matter, but in which case of course instead of a plate we are talking of a shell, but essentially it remains the fact remains that this is going to be thin. In other words, your thickness over here, or let me call it height to be consistent with the notation that I'll use later, will be compared to your length and your breadth. This is something we have talked about in terms of motivation for using plates and shells. We already said that your h has to be very small compared to your L and B, right? So, which is when we call this as a thin plate. So in that thin plate, along the length we have introduced a coordinate x1, along the width we have introduced the coordinate x2, and along its thickness or height we have introduced the coordinate x3, right? So now what we are saying is that these normal stresses sigma 11 and sigma 22 are of course normal, but they are also in the plane, that plane that we are interested in which we are going to make an approximation of plane stress. So that sigma 11 and sigma 22 is what we are saying are non-zero. In other words, automatically we are saying that these are the only 3 non-zero stresses. The other stresses are all equal to 0. In other words, anything which has a 3 subscript in them, those are all going to go to 0. So that's essentially your third, fourth and fifth members over here. All of them have at least one 3 as their subscript, and therefore they are involved with that third plane. Already we showed that this is sigma 33, which is equal to 0. What we are saying is that the shear that acts either in this direction or this direction, which is again a tau acting on the 3 plane, therefore the first subscript is 3. Now it's acting in the one direction, and therefore, so let me take this way, tau, this is your tau 3 along on the 3 plane in the one direction, and this is your tau which is acting on the 3 plane in the 2 direction. Okay, So on that plane, any stress will always have its first subscript as 3. Why? Because that infinitesimal element has a normal which is along the x3 direction, right? So because it is having a normal along the x3 direction, the first subscript is 3. The second is the direction which the force itself acts. So therefore the normal stress is sigma 33, whereas the shear stresses are tau 31 and tau 32. If you are in addition making a no body moment assumption, then of course this is equal to tau 13 and this is equal to tau 23 as well, doesn't matter, right? But essentially what we are saying is that these 3 quantities are all going to 0 at all points within the structure. And this is an assumption, again as I said we are putting in red, so it's kind of dicey, sometimes valid, sometimes not, what we call as an ad hoc assumption. So ad hoc assumption is a term this adjective ad hoc, Latin term, essentially means sometimes valid. But what people do is that they extend the validity where it is not valid as well, and that's where you get into the red or danger zone. And you will see that almost always in all aerospace structures, the way things are loaded and the way the materials are, you will see that these are not actually 0. In other words, these 3 together I can write a single term for that and call them as sigma I3 or 3I equivalently, right? In other words, one of the index has to be 3, the other can be any one of them, I equal to 1, 2 or 3, right? If I equal to 3, then it becomes a normal stress, otherwise it is a shear stress. And that shear stress that we have are what are known as the transverse shear stresses, and this 3, when you have I equal to 3, that's called as the transverse normal. Whereas these two, tau 32 and tau 31, are both transverse shear stresses. Very fact that the subscripts are different from each other means it's shear, which is why we use a tau instead of a sigma. But even if you use sigma, as long as the subscripts are different from each other, it's essentially a shear stress. It's just a matter of notation. But why both of them are transverse is that they are perpendicular to the plane that we are interested in. So in other words, they are acting on an element to which the normal is x3, which is perpendicular to both x1 and x2, which is the plane of interest for us. So in other words, instead of writing 3 equations over here, sigma 33 equal to 0, tau 23 equal to 0, tau 31 equal to 0, I can express the whole thing in terms of this single equation, sigma I3 equal to 0. That's all plane stress assumption is all about. It's essentially saying your sigma I3 equal to 0. Now what happens in reality? Let's go back to our example that this is the panel of let's say a wing skin, let's say on the top surface, without lots of generality. It could be either the top or the bottom, doesn't matter. But let's say it's the top surface and just one panel over there. What are the main loads acting on the panel as the aircraft flies? So there is an airflow which is happening over that, and that airflow is going to cause a pressure distribution on this, right? That pressure distribution, you can very easily see pressure is a compressive stress and it has to act perpendicular to the plane. So in other words, that is nothing but your sigma 33. So very easily you see that there is already a sigma 33 which is non-zero, which is present because there is a pressure distribution. It becomes worse when you go to the bottom surface of the wing, where the pressures are even higher compared to the top surface, which is why you get a positive lift in order to match the entire weight of the aircraft. So in other words, a very large pressure is acting over here, a smaller pressure is acting here, but both are non-zero, and therefore your sigma 33 is actually present. But you will see almost everywhere a plane stress approximation is used there, which is fine, because the other stresses, namely your normal stresses that we had started listing out, namely your sigma 11, sigma 22 and tau 12, which are your in-plane stresses, the last being an in-plane shear stress. So the difference between the in-plane and the transverse: in the plane there are two normals and one shear, whereas in transverse you have one normal and two shear. Okay, so keep that in mind. What we are saying is that in reality what happens is that sigma 11, tau 22 and tau 12 are typically of much larger value compared to your sigma 33, tau 23 and tau 31. Even in the example that we talked about, where we say in the bottom surface very large pressure is acting, even in that the sigma 33, yes, it is non-zero, it is a large value, but your sigma 11 and to some extent sigma 22 also will be much larger, especially sigma 11 will be much larger than sigma 33, and we will see soon why that is the case. Okay, but keep that in mind. Once we come to that particular expressions for sigma 11, we will see that it's actually the way it is related to the pressure. It will involve an amplifying factor which is going to make it much larger than sigma 33, and therefore this actually holds. But what is the assumption saying? It's not saying it's much greater than, it is just saying it is equal to 0. Okay, that's the problem. It's not equal to 0, but it's very small. And when we are saying very small, it's relatively speaking compared to sigma 11, sigma 22. If you are taking that alone, it might seem quite high. Just that it turns out to be much smaller compared to some of the other stresses, and therefore I can say that those are very small, these tau sigma I3. In reality, I can call these in-plane stresses, instead of writing them as three separate terms, I can just call them as sigma alpha beta. Whenever I use Latin indices, they go through the entire range 1, 2 and 3. When I use the Greek subscripts, all Greek subscripts will take only the two values which are within the plane, 1 and 2. Okay, so whereas we will let me not confuse you, I'll come to the fiber composite later. Right now it's an independent assumption that we are making. The seventh assumption is independent of the other 6, just like all the other assumptions were also independent. We are not combining that with this right now. We are only focusing on the 7th assumption, which is the plane stress, and there we are saying that I can club all the transverse stresses, the one normal and two shear, into one expression sigma I3 or tau 13, however you'd like to call it. Then the other, of course, is your sigma alpha beta, which is again having 3 terms, because alpha and beta can take on 1 and 2. So therefore there is a sigma 11, there is a sigma 22, tau 12. Of course there is a tau 21 also, but we know that they are equal to each other if there are no body moments. So therefore, because already we're talking of a Voigt notation, so this is the Voigt notation that we talked about earlier in today's class. So we are saying that there are not 9 stress components, only 6. So we are making one of those assumptions in addition, that assumption number 5 that is already there, right? So now we have these 3 going to 0. Therefore we have already gone from 9 to 6. Now 6 out of 6, we are saying 3 are zeros. So we are left with only 3, and those are these in-plane stresses, which we can use a common notation to describe all of them as sigma alpha beta, where alpha beta can take on values 1 and 2, right? So to put this in a proper perspective, this is what the plane stress ad hoc assumption is. So the ad hoc assumption that in plane stress is to take sigma I3 equal to 0. But what is the reality? it is that this is much greater than. So I can write that same thing in a different way, that sigma I3 is very small compared to your sigma alpha beta. So this is reality with a lot of plates. This is not reality always, it's just reality wherever most people are taking plane stress approximation. You will see that maybe this is true, and therefore it is a reasonable approximation to have. But the problem is when they actually set it to 0, in which case there are a lot of contradictions that happen. What are those contradictions? Let's see. First, are there any doubts on this so far? First thing is, when we get back and reintroduce all the assumptions and take it along with that, one of the things, or even before we get there, we already said, for example, in the wing panel that there is a sigma 3.3, right? Now that's a boundary condition. So in other words, what are the contradictions because of this? There are many, but three main things we will list over here. The contradictions with reality. Okay, so the first thing is that the boundary condition is violated, because most plates are rarely, like you can think of the plate on which all of you have your laptops. You're essentially having that laptop has a certain weight, your water bottles have a certain weight. Now all of those are perpendicular to that, right? Perpendicular to the plane of the table. In other words, if I apply for this particular structure the boundary condition where your laptop or my iPad is, essentially there is a normal stress which is in the 3 direction, because x1 and x2 are along the, x1 is along the length, x2 is along the width or breadth, and x3 is along the thickness. Now you can see that this is putting a weight downwards which is along the x3 direction, and the normal to this surface is the x3 direction. So on the surface to which the normal is x3, there is a pushing load which is along the x3 direction as well, which is essentially a stress sigma 3.3. Now that stress sigma 3.3 obviously is a boundary condition for this particular structure, and that boundary condition is violated. Or coming back to our aircraft example, if this is the aircraft wing panel, let us say, and the aircraft is flying, then you see that on the panel there is not only a flow because of which there is a pressure, but that same flow, because it is viscous in nature, it's also rubbing across the surface and creating what we know as a boundary layer. Within the boundary layer there are viscous forces. Now these viscous forces are nothing but shear stresses on that plane, which is erase that picture, but essentially your tau 3.2, because on the 3 phase in the 2 directions along the width, which is the chord of the wing, which is essentially a tau 3.2 which is present, and tau 3.2 cannot be present according to this, it's saying it is equal to 0, or sigma 3.3 also is 0, in other words the pressure. So boundary conditions, both normal and shear, are both violated. Okay, so this is, for example, pressure distribution, and this is, for example, a viscous stresses in the boundary layer. Okay, so those we know are present, they are not 0, but we are assuming it to be 0. So in other words, right from the simple mathematical model, we are not allowing for the boundary conditions to be respected. So not just one boundary condition, but boundary conditions that are violated both in normal and shear, right? BCs rather than just the BC, right? Now that's one contradiction in reality. The second contradiction is that there are certain equations which are called as the compatibility equations. We will look at them a little later. And the reason for their presence is that there are only three displacements. In other words, three components of the displacement. Let's say U1, U2 and U3. And in terms of the derivatives of which you're actually expressing 6 strain components So gamma 11 for example is just in a linear strain displacement relationship. Gamma 1 is dou U1 by dou X1. This is dou U2 by dou X2, dou U3 by dou X3. This is dou U2 by dou X3 plus dou U3 by dou X2 and so on and so forth, right? So now you see that all 6 of them are defined only in terms of 3 quantities. Of course, their derivatives with respect to x1, x2, x3, but only 3 variables are defining 6 variables. So obviously, all of these 6 cannot be independent of each other because they can all be obtained just from 3 fields. 3 displacement fields are defining 6 strain fields, right? So, which means that these are not independent, and the way we connect them with each other using the definitions that I just reeled out, dou U1 by dou X1, etc. For example, the last one is dou U1 by dou X2 plus dou U2 by dou X1, right? So all of them are defined in terms of U1, U2, U3. So I can take the second derivatives of those and then I can manipulate these equations to show that yes, there can be 3 compatibility equations. And you would see that if I were to take this and then apply my constitutive law, I would see that those compatibility equations are also violated. Already we were violating the structural boundary conditions. That's at the level of the structure. We saw, for example, the wing panel, the pressure and the viscous shear stresses, especially for fields which have low Reynolds number. So when you have low Reynolds number, you will have this quite substantial. So already we saw that that is being violated. Now we are seeing that from a purely structural point of view, even a purely mathematical point of view, we are seeing that the compatibility equations are violated. The third thing is once we combine all of those together, because we want to deal with composite structures, which is pretty much the normality or the which is very common in the aerospace industry, then you would have not just a single plate that we were talking about earlier over there, but we are going to have layers within that, what we call as a laminate. See an example of that over here. The top one is having 90-degree fibers with respect to an x1 direction. The fibers are at perpendicular to that, so it's 90 degrees. Then you have plus or minus 45 degrees over here, and then you have 0 degrees over here, which is 0 degree because it's parallel to the x1 direction. Here it's along x2 direction, therefore it is 90 degrees. So whereas in these two, it's making an angle between 0 and 90, so you can say approximately plus or minus 45 over there, because it's in 2 different directions, it's crossing with each other. So now almost always you will have multiple layers. Even if all of them are 0 degrees, you would still have multiple layers stacked to each other, joined to each other, because each ply by itself is fairly thin and it cannot take too much of a load. So you typically will have in most aircrafts, like let's say passenger aircrafts like the Airbus aircrafts or the Boeing aircrafts, many of them will have about 80 layers, 80 or 100 layers. Okay, depending upon how large the stress or strain is at that particular thing, you might have like that. So essentially what is happening is between these layers there is a possibility of they getting debonded, and that is very common. It's actually witnessed in actual inspections whenever people do a non-destructive evaluation, or they open up an aircraft just to test what has happened to some of the panels when they want to replace a panel at a particular maintenance frequency, etc. You will see that many cases, either at the edges or somewhere in between, the bonding has given way. When can that happen? That can happen only when on that interface there is a stress. If there is no stress on that interface, this can never happen. Now, what is that stress actually doing over there? It's actually causing a debonding, which means that it is opening up like this, right? In other words, what we call as a peel stress. Now, that peel stress, once again, x1 is along this, x2 is along this, and x3 is along the thickness direction. So you can see the interface, the normal to the interface is along x3 direction. So all stresses which will act on the interface between any two layers is going to be a stress which is involving one of the subscripts as 3. If it is normal, it is sigma 33, the transverse normal, which is causing a peel stress. And if sigma 33 is large enough compared to the strength of the bond, that is essentially the bond is the epoxy matrix or whatever matrix is used for the rest of the composite, it's the same thing in excess, which is essentially bond. Now, if the bond strength epoxy is exceeded by your sigma 33, then it's very clear that it's going to peel off, right? But, and we see this quite often, that it is peeling off, which means that there is a sigma 33 which is present, which is not 0, and in fact it is large enough to be larger than the peel strength or the bond strength of epoxy or whatever the matrix is. So it's quite clear that the assumption sigma 33 equal to 0 is no longer valid. Many a times the delamination, as this is called, debonding between layers, is not happening because of sigma 33, but it could happen because of a sigma 13 or a sigma 23 being larger than the shear strength of that bond. So that bond also has a shear strength. It cannot hold stresses beyond a certain value. Obviously, that is getting exceeded. Now we know that those stresses are tau 13 and tau 23, and those are precisely the stresses which we have set equal to 0. We have said sigma 33, that is that peel stress, is equal to 0. We have said that tau 13 and tau 23, which are those transverse shear stresses, are equal to 0. According to this ideal model, I should never ever have delamination. So I can be happily resting with any laminate that I create. I don't even need to probably put excess resin between them. I can rest assured that it is happening. But that's not the case. That's not what reality tells us. Reality says that yes, sigma 3 is small compared to sigma alpha beta, but it's not 0, not exactly 0, which means the third thing that is happening over here because of this particular assumption that we have is that delamination can't be modeled. Leave alone can't be modeled, it can't even be detected or can't even occur according to this particular model, and which means that it's going to be, oops, sorry, forgot that we exceeded the time. So let's split for lunch and then we will reassemble at 2:30. Do let